This is how and why my year has been going this way. I very cunningly devoted over 20 minutes this morning to gathering some images for my talk this afternoon and put them on a thumb drive in my computer in my bedroom where it now resides. I could have put it in my pocket if I had just taken it out of the little plug. Here we've got a brand new Bramo motor. Bramo does some electric motorcycles, and Steve West, I think, has a video documentary of the Isle of Man race. Is it Nick Smith? And that we were going to watch last night, maybe we'll tonight. But electric motorcycle racing is quite exciting. Bramo is one of the leading players in that race to such success that they were purchased by a company called Polaris, which is the arm of a company called Bombardier that does not make Learjets or snowmobiles. They bought the global electric motor car company, Fargo, that did the gym. And my first EV in this epoch was a gym where I took some Maxwell capacitors, some Trojan lead acid batteries, and some new Chinese Satan lithium cells in 2008, and played with them quite a bit, and decided that the new lithium batteries might be good enough for a car. Brian, get me a car. And I had almost no interest in cars at the time, and we did an electric car using them, and that set us off there. I don't like motorcycles, and I don't like electric motorcycles, and that's because a guy who has 7 airplanes should not be killed on a motorcycle. It's bad karma. But they are a lot of fun, and a company bought a bunch of these from Bramo. They retail, if you qualify as an OEM, at $3,600 a piece. I bought them quite right. I got 6 of them, and show special. Any of you that wants one, I'll let it go for $2,000, which is their 100 and above price quantity at Bramo. And I have 6 of them. They don't have an inverter. I talked to Brian Hall yesterday. I don't know if I was going to buy some EVCON inverters from him or if I was just going to send people to him. He has an EV components company that we've traded back and forth with since the beginning. And it really hardly does electric cars anymore. He's out in California and has found quite a bit of life with sailboats. And so he actually is a EVCON distributor, and their EVCON Gen 4 is available in 48 volts, 72 volts, 96 volts, 110 volts, I think, and any of those will work this motor. It's 40 kilowatts peak, 25 kilowatts continuous, liquid cooled, and weighs 32 pounds. A little over 32, so 16 kilograms. It's 10 inches long and a 7-inch diameter motor. Internal permanent magnet motor, meaning it uses permanent magnets in the rotor, and they're kind of buried rather than on the surface. So very high power for its physical size. Probably not good for a car, but if I'm left with one, I would be tempted to do a 1960 Hudson Metropolitan, Nash Metropolitan. With that, retaining the transmission, simply see if I can make it work.
What voltage is it?
It will go up to, he said 700 volts. So I'm not sure. This was kind of a specially made version, for this pump company, and but it has kind of a universal threaded keyed shaft that normally you put a motorcycle sprocket on, but you can put a number of things. It's an AC motor, but it's a permanent magnet AC motor, and the inverter has to be tuned to the motor. We have a spec sheet with actually what those figures are that you need, but Brian Hall will set up a EVCON for you on it pretty easily. In fact, he's wanting to buy one. So $2,000 until Saturday morning, and after that, I actually already have them on the website. I put them up this weekend, but we just got the motors a few minutes ago. Let's talk about CAN. A good part of our sessions this week are going to be about CAN, and I have some neat stuff going, primarily in two areas. Colin Kidder has come of a large distance on a couple of software tools called the Generalized Vehicle Reverse Engineering Tool, and an associated connected laptop application called SavvyCAN. The CAN community is actually quite small, so the 800-pound gorilla is a company called Vector. I guess their base product is called Canalizer or Canoe. It starts at about $5,000, and by the time you have the full suite, you're at 11, 12,000. And all this makes perfect sense because there's about 80 people in the country that know what to do with it. And now we're hoping 130 people after this week. And increasingly we get more interest in the EVs in CAN for reasons I've already explained. Colin has duplicated 60% of the functionality of the whole Vector suite in free software. And we've duplicated the $1,000 Kvaser in $150 worth of hardware. And so we can talk to CAN, and we can analyze CAN, and we can do some neat things with CAN. So that's why I'm a little excited this week. I've got a complete unknown. I just kind of lunged at this. A guy did a book called CAN Hacking Your Car, 2014. It's almost a pamphlet, but it's sold well on Amazon. And he kind of stole the show at a show called EVCON. EVCON and BBSCon started the same year back in the early 90s. They were more about anti-software protection in those days, and bulletin boards. And we were about bulletin boards. But they've grown up to be kind of a hackers convention. They contacted me soon after they had their DEF CON this year, because we had done the announcement on the Tesla drive unit. They had Tesla at DEF CON, and the guy who stole the show was named Craig Smith, and he is the author of the book, and did a kind of they had a car, and he did a hacking, how to reverse engineer the car type thing. I've never heard him speak. Turns out he has a consultant company called File Labs, and is a little, when I described to him how we didn't really fit all that I read about him, he said, well, actually I don't either. They do more consulting on the security side of cars than anything else. But I suppose it's kind of like the guys that sell the antivirus software, and you catch them later releasing viruses. Guy in the glass business who gives away BB guns to kids. So he will be here tomorrow, and I have him slotted for 2 sessions. So I wanted to do a presentation on CAN that is technically inaccurate and quite misleading. And the reason I want to do that is because the real presentations on a CAN don't have very much to do with how it's actually used. This is a CAN network, and this is a CAN node. Let's call this a charger, and this is a CAN node. Let's call it a accessory power module, and this is a CAN node, and I'm going to call that a windshield wiper. And on the two ends, we have our term, which is a CAN network needs to be terminated, and those are 120 ohm resistors. And of course, it shows that these are not terminated. In practice, every time I've not terminated anything, it hadn't worked. Anytime I have terminated something, it's worked great. And if everything's terminated, it still works great. So I just terminate almost everything. It's two wires. And the reason it's different from Ethernet, RS-232, or anything you're familiar with, is that both wires are simply 2.5 volts. And when you put a digital 1 on them, one of them goes to 3.5 and the other one drops to 1.5. So it's a differential voltage between the two wires. And when you go to 0, they both go back to 2.5. And if you twist those two wires, it tends to cancel out any inductive pickup from the AM radio station, which is your DC motor. And so it's somewhat resistant to noise. CAN was proposed, invented, made up by Robert Bosch in 1986. And the whole concept was we keep adding stuff to these cars, radios, serial lighters, and so forth. And with each one of them goes some copper wires. And copper wires are heavy. They're getting increasingly difficult to route in a manufacturing sense. The CAN was devised purely as a copper weight reduction scam. We'll take two wires and run them, the same two wires to everything, let them talk over that, and give everything 12 volts and frame ground. And basically we have 3 wires to every device on the car, but we don't have to go back and forth in all the endless combinations from one device to the next. They're on a common bus. And he wanted it to be like RS-232, but noise resistant, and that's where the differential came from. That's what a CAN bus looks like. Let me see if I can show you what a signal on that bus looks like, and all the many parts of it that we want to ignore entirely. But it would be kind of cool that you knew vaguely that they were there. And here is our differential. Notice all the noise, which we don't care about, and it's going to affect us because we are differential at 3.5, 1.5. Here we're at 2.5 both, back, both, and so forth. Let's talk about the CRC field. CAN has a plenty of error detection, the cyclic redundancy check in the message itself. And that is handled between the two transceivers. Your software, your microcontroller never needs to deal with any of that. And we keep finding CRC and checksums in CAN messages to make sure the message is correct. I have no idea why. I would think of this as being hardware. It's actually not, it's software in the transceivers that does more than adequate error checking. And that's it. This is the arbitration field. It's actually the message ID. The message IDs are very important. It's the only thing that tells you what the message is about. That identification, that number, the medium is the message. All the information you need is really contained here, and it can be 11 bits or 29 bits, and they're both used at random, but most of the stuff we see is 11-bit. And we would represent that as a 3-digit message ID. The first digit, since we're limited to 11 bits, is 0 through 7. It could be any of that, plus 2 digits, hex digits between 0 and F. So 000 to 7FF in hex. And why do we use hex? I take an 8-bit byte and convert it into 2 4-bits, and that will give me values from 0 to 16. And so we use a base 16 numbering system, 0 through 9, and A, B, C, D, E, F. And so at a glance, I can tell that the left 4 bits make up a 7, and the right 4 bits make up a 9, or an E and an F, or whatever. So it makes it easy to go back and work the binary. So this is the address, can be 11 or 29. There's 4 control bits. They don't, they're not very important. There's an RTR bit. CAN has provisions where you can send an inquiry and get a response. Nobody ever uses it. They do inquiries and responses, but they add another protocol layer on top of it, like J1939 or CAN Open or something else. So you almost never see anybody use this control bit. We do have a, in this, the number of bytes of active payload. And here's our data, 0 through 7. 0 being the least significant, and 7 being the most. And that 0 through 7 thing causes some confusion. All of it in computers generally is numbered that way. The first one is 0. I mean, it's not counting 0, but we always do. Why is that? Well, you start with a 0 state. If they're all zeros, it's 0. 8 is the maximum number of data bytes in a message, but you don't have to have 8. And we do have a byte that tells you how many bytes are active in this message. Often, what you'll see is that set to 8 and they only use the first 2 bytes. Which causes some problems. We've run into it with EVCON. So what do you do about those if you simply leave them at what the last message was? It almost makes it look like you have some information there. If you zero them out, or you set them to all Fs, or what. But that's very commonly, they'll designate 8 bytes, but 6 of them are reserved for future use. Which makes no sense, but this is just, what I'm trying to do is relate what people were really doing with this against the CAN theory. You can go to Wikipedia, get all the CAN theory, there's a number of things on there. They talk a lot about these different bits and end of frame and stuff. You'll never see it because it's handled in hardware anyway. What you'll see is the message ID, the number of bytes, and the 8 bytes. So that's, and the ID can be 11 or 29. On the bus, and the bus can be a number of speeds, but the differential buses are typically 125 kilobits, almost never, 250 kilobits, a lot, 500 kilobits, a lot, and 1 megabit, not very much. So anybody on that network, those nodes I showed you, can simply issue a CAN message at any time. And so like Ethernet or any other protocol, you have collisions. And this one's real simple. Here's your address, lowest number wins. And you can actually be transmitting at exactly the same time. And when you get to the bit where the one guy is 0, he wins. And that's the end of the arbitration. So the only rule you need to know about arbitration is the lower message wins. So if you see CAN messages with low IDs, 0 springs to mind, or 1, those are very important messages because they have the highest priority. If you see 700 series messages, it means if we didn't do any of these, the equipment will probably work fine. We're not too sure why we're putting all this crap in here. and then they fall between that. And so that's your message structure. For our purposes, 11 or 29-bit message ID, the most important thing, a byte indicating how many bytes of active payload, and then 8 payload bytes. Most of the rest of this does not appear in your software. It's done in hardware by the transceivers. And CAN, to affect CAN, you have a controller chip and a transceiver chip. I don't know why, but everybody splits it up that way. On the Arduino DUI, the controller is built into the SAM3X, and then we add a transceiver chip. So on the bus, we're receiving messages. The arbitration, the CRC, the end of frame, the bit stuffing, I won't go into, is all handled by the transceiver. You never see it. You'll never see it in software. You can't access it. It doesn't exist for you. And all the explanations that CAN spend a lot of time on this. Very few people are involved in designing CAN hardware, transceiver hardware. So I think they're just repeating the shit they read in the last book to be thorough. But you don't need any of it. Do be aware it happens with all that CRC. Why are you checking to see if the bytes are right? The transceiver already did that. And in fact, one of the magic aspects of CAN, I think, is almost all of the CAN chipsets have filtration masks and filters built in. And so you can program the hardware to where all CAN messages are entirely ignored and do not exist except for the following 4 messages or 6 messages, or all messages above 600, all messages below 100. You can mask and filter this actually in some pretty capable ways to where an interrupt will not be generated and the byte will not be passed to the controller and onto your multi-controller unless it's one of these messages. It's not that you may be free to ignore them in designing your software. You'll never see them. Again, at the hardware level, they're masked out. They do not exist. And the central thing about CAN, and what I like about CAN, is this sort of blind reliance on the fact that the receiver knows what to do with the information. The transmitter knows how to put the information in there. This one's going to issue a message 400 with 8 data bytes of information. And it knows to put the first 2 bytes to represent voltage, and the second 2 bytes to represent current, and the third 2 bytes to represent temperature, and the fourth 2 bytes to represent time of day. And it puts it on this bus, and all the nodes ignore it completely. In fact, they don't even see it, except for the one at the end who's set to mask through 400 messages. And it knows in its firmware, in its software, what the first 2 bytes are for. They're for voltage. What the next 2 bytes are for, they're for current. And so you have 2 devices on a bus that simply by identifying the message as 400, they know what to put in it on one end and they know what to take out on the other. And the other devices on the bus are not even aware 400 got transmitted. They don't even see it. Isn't that cool? And so when I say the medium is the message ID is the most important information in the transmission. Much more so than the data in the 8 bytes, because that defines the topic and what you can use this message for. And indeed, in normal practice, the other devices would typically be filtered to where they don't even know that message was ever put on the bus. And so all the intelligences are on the end. This is the dumbest protocol I've ever seen. It carries no information in it other than a message ID. And so that's the basics of a CAN network. Let's see. I think I say I left most of my images at home, and it doesn't matter a lot.
Hey, Jack, how do they keep from stepping on each other?
They don't. They step on each other all the time. I apparently glossed over that with an inadequate explanation. This message ID is the arbitration. The ID itself is the arbitration. And if you start where we're both transmitting 1 bit, we're both live. And when the next bit we both transmit 0, we're still tied. And on the 3rd bit, this one transmits a bit and this one transmits a 0. End of time. The 0 wins. And so if your 2 messages are stepping on each other exactly, 403.3FF, 3FF wins every time. And as soon as it wins, the other one stops transmitting. That is the bus arbitration. Is that not elegantly simple? It's cool. It's better than what Bob came up with for Ethernet, I think. You got to be pretty quick in the transceiver to be able to do that, but they can. And again, time zone wise, this is 500 kbps for a microcontroller even. Very slow. You can do a lot in between bits. Steve?
Yeah, the only reason it works is because it's so slow. You can't run that kind of arbitration over Ethernet because of the...
Right.
You've already sent the message before the other end has time to realize that it's clashing.
Yes.
Yeah.
Yeah, it's pretty basic.
But it means you cannot run CAN bus any faster than the,
1 megabit.
Right.
Can or can't. I understand what you're saying.
Yeah.
As soon as we do that, next week somebody will have a 5 megabit can. But
Sure. Running on fiber
I
optic.
mean, I quit telling people they couldn't do shit a long time ago because some of them take it as a good cue to go do that. Perp.
Actually, I know from the commission at Volvo that they are moving away from CAN now to switching Ethernet, which is TCP/IP protocol for cars. They use quite a lot of, because they can go up to 100 megabits.
Yes, the bandwidth is hugely higher. And there's been actually that friction between the two for a long time, 20 years.
Yeah.
It's the inertia of some industries is impressive, and in the case of the automobile industry, awe-inspiring. And so the bet that it's all going to be Ethernet is a sure bet, except there's very few of us in this room that will live to see it. These things move slowly. You'll see hybrids along the way. Tesla has a lot of Ethernet in their car, but it's all glued together over CAN.
That kind of defeats the saving the wire thing, because Ethernet you need a router or a hub, and everything's got to come back home to it. It's not, you can't daisy chain along the way. Unless they've invented daisy-chained Ethernet, which is...
Well, Ethernet is kind of, Ethernet started as Aloha Net in Hawaii, and it was actually wireless. And everybody threw packets up in the air, and the ones that got through kind of got through. Bob Metcalf invented Ethernet and teaches at the University of Austin, and used to be a almost perennial speaker at EVCON and ISPCon. I've known him for decades. What Pert's alluding to is because of the bandwidth advantage, inevitably Ethernet will win in the car, as it's won everywhere else. The pace at which that'll be done, you understand the investment in hundreds of sub-suppliers. You're talking about windshield motors and EPAS, electronic power assisted steering, and tire monitor pressure, and DC to DC converters, and speedometers, and fuel gauges, and it's a big industry that it took from 1986 to really, it was well past 2000 when CAN really took hold in automobiles. It's a 20-year process with a whole lot of suppliers that have to start supplying components that are CAN compatible, or you have to run wires to them. And it was kind of knocked down one at a time. Windshield wipers were still analog, just 12 volts and a switch, and so, until they weren't. And power door locks and power windows, the same thing, and the radio and the stereo and the telephone and the knobs on the steering wheel. It's been one at a time that this CAN progression has gone over. So Ethernet is better, so it's going to take over CAN. True. Why would I care about that? I've been dead 12 years by that time. It's, and it'll take a long time for that to happen. But you will see hybrids right now. He's not predicting a vague future. This is already going on. And the Tesla has at least one Ethernet bus, and maybe two, and 6 CAN buses. And so that's the nature of it. But I wanted to do a brief introduction to the structure of a message and how these devices can all be on a 2-wire bus, coexist, and pass information to each other. That's because there is no central computer, really. There is no central authority. There's no router. It's not arbitrary. It's just 2 wires, and you can plug in something to this 2 wires without the car's permission. There's nothing anybody can do about it. And you can read every message that's on it, and you can put messages on it. And you're just as legitimate as the VCU in the car. It's not, you're just as legitimate. Nothing in the car can even tell that you don't belong there. It's very basic. And the effectiveness of how to make things happen is carried in the message ID itself. The same thing that does the arbitration entirely defines what the message does and what its data is about. And you have to know that on the other end to get anything out of it. There's no magic protocol defining the order of bits or bytes or JPEG or something here. It's just 8 data bytes. They can be anything. They can be one 64-bit number, 2 32-bit numbers. You could have it be, every bit of it be an individual meaning. The entire 8 bytes could be just 64 bits, and each bit represents a state. You can arrange them any way you want. You can have them be least significant byte first, or most significant byte first, or I mean, it's just 64 bits that you can use to represent data. And that leaves the door open to the higher protocols, which can then take that granular item and recombine it into larger things. And we can say that, you know, 6 frames, the 6 sequential frames of the same message ID with a counter in byte 0 can give you the order, and that can be paragraphs of data. But those are higher order protocols over the top of CAN. And you'll hear that discussed as CAN open or NEMA CAN, green stuff for boats. Different industries have different further protocols for CAN, which Mystify me and Colin may address some of that later in the week. This is the basic, here's what CAN is, and how to think about it as a practical matter if you're either trying to reverse engineer or write software for it. You don't need to worry about the CRC field, the interframe, the bit stuffing, really the control bits, or what voltage the CAN protocol's at. It's a message ID that defines what this message is about. And the corollary to that is it actually defines who gets it, and that's who listens to it. And then whoever is listening for it should already know in their heart of hearts what to do with that 8 bytes. That's not transmitted, that's carried in their firmware, at their microcontroller. It's not on the bus. On the bus is just the bytes. All the intelligence what to do with that is in the firmware on the receiving device. Master slave, sender receiver, to some degree on the upper level protocols, but on basic CAN there really isn't any such thing. Anybody can send, anybody can receive. Everybody can send and receive. Some devices only receive, some devices only send. But there's no assignment there. You can send, you can receive. The traffic is bidirectional. The information is bidirectional. There's nothing inherent in CAN about a master or a slave or a boss node or the router. It's just random.
But still, a transceiver is expected to stop transmitting if it's overridden due to the known higher priority message.
Yes, it will observe bus arbitration.
Yes, that's important.
If it's trying to transmit, will it hold that message until bus is cleared and it's got the priority? And then
Yes,
transmit
at the transceiver level, you don't have to retransmit. You do not have to retransmit a message that got stomped on. That's handled at the hardware level.
Yeah, so some message IDs are more equal than others.
Like Animal Farm, some are equaler than others.
You have frames, you have a fixed frame like both. That's what I understand. You said?
It's fixed, but it has two styles, 2.0 and 2.0B. That is 11-bit identifier and 29-bit identifier. And all 29s will observe 11. And so you'll often see the same bus with mixed message ID links. That's not uncommon at all. Colin?
So one of the things you didn't cover, it's kind of related to arbitration and such. There is, at the end, you can't really see it on there, called the acknowledge bit.
Mm-hmm.
And the CAN bus transceiver looks for that. And one of the things, the way that arbitration works, the CAN bus transceiver, while it's sending, is also reading at the same time. So the CAN bus transceiver knows when it sends a 1, is a 1 on the bus or is a 0 on the bus. That's how the arbitration works. But it looks at the acknowledge bit, and if a node accepts a frame, it sets the acknowledge bit. You could have 50 nodes all set the acknowledge bit. As long as somebody does it, the transceiver will know that the frame was properly sent and it won't try to resend.
Okay.
If nobody acknowledges, it may try to resend over and over and over and over because nobody's paying attention. But that's also a configurable setting. The transceiver does not have to resend. You can turn that off. You can send only once.
It's a good point. Don't get too bogged down in it. But what he's saying is, big blast of the horn or some big noise event on the bus, the transceivers will automatically transmit until somebody acknowledges it. But that's at the hardware level, guys. You'll never have to deal with that. You'll never have to make any correction in your software or any provisions for it. You'll never see it reading canned messages. It's at the hardware level. That's a protocol level you don't get to look at, actually. I guess Colin has to a little bit in doing the library, but since he did a good enough job of that, I don't have to. And by the way, you're probably unaware, but I don't even think Colin knows how revolutionary, how much it has revolutionized the entire automobile can scape. A little Arduino library he did for it. And every time I revisit the base Arduino CAN library, I'm reminded of how wretched life can be.
So, Jack, one more question, and it's going a little far afield. But with this auto drive feature that you hear about in the Tesla S's, which protocol do you think they're using to enable that? CAN or Ethernet? Which do you think is more reliable in that sense? Or I'm sure you may not know, but I just...
I'm going to say I don't know. That's a good answer, and I like that answer. It saves a lot of time. I happen to know the real answer, and it's CAN, but I'm going to go with I don't know. And part of the reason is that all that sort of a combination of new and old that's changing. Many of the sensors have been in the Tesla Model S all along.
But I'm just thinking, you'd want something that's most robust and reliable, in terms of microseconds or milliseconds response time. Speculate.
Time zone is, to me, the heart of the magic of computers and software, and the easiest thing to get tripped up on. And it's kind of like my description of charging and discharging batteries, that time zone does matter. I'm going to let that drop. Computers work faster than we do. And my first assembly language program, believe it or not, was an attempt at a word processor on a Sinclair Z80 at 4 megahertz, which is a fraction of the 84 megahertz available on the Arduino Dewey. And I wrote the same piece of software 4 times to move a cursor from one character to the next on a line of text. And for some reason I made some error in it where it would only appear on the leftmost position on 80 characters or the rightmost. And so I rewrote it and completely differently. And with the result that it would only appear on the leftmost character and the rightmost character. And so I rewrote it completely using some wacky, nobody should ever write software this way, but it came out that the cursor could only be seen on the leftmost character and on the rightmost character. And so I wanted to slow it down, and so I put in a loop that counted to 256 and stuck that in there between each character it was supposed to hit. And the cursor would appear on the leftmost character and then the rightmost character on this line. So I made another loop that counted to 256, but each time it counted one, it called the other loop that counted to 256. And I tried that, and it was working okay, except the cursor would only appear on the leftmost character and the rightmost character. And so I put in another timing loop of 256 to call the one that counted to 256. They called one that counted to 256, and the next test, it would only appear on the leftmost character and the rightmost character, but something would flicker in between. There you go. And by adding 8 more levels of counter. I got where it would only streak across the screen. The first software I wrote worked fine. It was so fast I couldn't, it's called debounce on a key. I couldn't get my finger off the key fast enough to stop the cursor. And so there's a huge disconnect in time between your mind and what happens in a computer. Now, this is 500K, and Ethernet is now up to gigabit in the home. And which is the most, what did you want, robust and, yeah, I don't know. I'm gonna go back to I don't know. Colin, do you know?
Well, CAN bus is a lot more robust. That's why it's used in cars and not Ethernet, because Ethernet in reality is garbage for being reliable.
The heart
It's
is the
fast,
differential
reliable.
pair and the twisted wire. I know that sounds trite, but it's actually enormously powerful in an automotive environment. The differential pair, you don't have a 1 and a 0 compared to ground. They both move, and you're measuring the differential, and you can twist them, and they still measure the differential, but they cancel out inductive pickup. And so that Robert Bosch's original design was pretty good to survive in an automotive environment. Can Ethernet be adapted to that? And I've seen Ethernet do a whole lot of stuff since Hawaii. And there was a long running debate whether Ethernet could be switched to gigabit speeds at all. And now it's $39.95 for a switch for in your house. So my answer is I don't know. But for right now, CAN is the most important game in town. Any other questions?
Yeah, there's one thing I was kind of curious about. You're talking about how the CAN high and CAN low buses can be either alternatingly at higher voltage or lower voltage. I'm wondering if you know of any situations where a so-called floating condition with both of them at 2.5 volts is ever used to represent any kind of information. Like, is there, in addition to 0-1, is there also 0-1 in float, or is that not used?
Complex question. The floating, the 2.5 volts, is the 0.
It's the 0.
No, it's the 1.
Is it the 1?
It's the
Colin?
one.
It's the 1. And the 3.5, 1.5 is the 0.
Oh, so there's not an opposite 1.5 reading.
No, because that would cause a short if they were trying to transmit a 1 and a 0 at the same time. So it's passive. The ones
But
are
that
passive.
said, we have single wire CAN or LIN, and that uses ground as the alternate line. And it's limited to much lower speeds, typically 33 kilobits, and that's why. Anything else? The basic architecture is 2 wires, connects a bunch of devices. The knowledge of what to do with the information is in the message ID, and you get 8 bytes to carry it. And there are higher level protocols layered over the top, the most famous being CAN Open at this point.
Now, I'm curious, do any of the elements in the CAN network, like poll all its constituents or something, or do they just sit there passively and wait for input to come by from somebody else?
All of them can transmit, and all of them can receive.
Yeah.
Once you've established that, and this is the basic CAN, in your software you can do a lot of stuff. You can say, I'm going to transmit a heartbeat message every 80 milliseconds. And if you don't get one from me, there's a problem. But that's in the intelligence, in the firmware on the ends. Anything you define at 2 points becomes true in CAN. And if it can be transmitted in 8 bytes or 64 bits. So you can make up a heartbeat. You can do a lot of things. And what we see a lot of is CRC bytes that don't make any sense. It already has CRC error checking at the hardware level. Why are they doing this? Usually to keep us out. really doesn't have anything to do with data integrity. But it might be that some of the engineers writing the software don't know that there's CRC, so you do know. At the hardware level, there's a cyclic redundancy check, a fairly good one, done on the data passing over the bus anyway, and that's all worked out before they pass the data to you at the application level. But you can make up all kinds of stuff to do. Just say, hey, if I don't get a message every 100 milliseconds, message ID 400 ID, I start the auto self-destruct sequence. And if James Kirk doesn't send one pretty quick, it's going to go on. That's entirely up to you. You can do that. Any other questions about the basic CAN? Let's take a break and come back, and I'm going to show you just a basic Arduino program, talk a little bit about Arduino and how that fits in with what we do.
What time do you want to start, Jeremy? 15 minutes?
Yeah, 15.
Digital.